Hello guys, welcome to our next video about the nervous system. In today's lecture, we will be discussing about various types of synapses and various types of neurons on the basis of their structures and functioning. So as you might recall from our lecture 1 of the nervous system, I'll give you a quick recap of what we did. This was basically the structure of neuron that we had discussed. These are the processes called dendrites, which will join to form the bigger processes called dendrons. So here are the dendrites and these are the dendrons, which will join to form the cell body in the center. Now from the cell body, here was our long process axon with the exolemma and the exoplasm in it. Then the axon is going to divide into branches called the telodendria, also called the axon terminals. The telodendria, I told you, will end in the form of rounded ball-like structures, which are called the synaptic end bulbs or the synaptic knobs. Inside these synaptic end bulbs or knobs, we had the neurotransmitter chemicals stored, and the neurotransmitter chemicals that are stored over here would also be covered with lipid membranes. The lipid enclosed neurotransmitter chemicals are called the synaptic vesicles. Here is the synaptic vesicle. So this was our discussion in the previous video. So let me take you forward now to what exactly is a synapse and how many types of synapses are possible in our body. If you look at this membrane, the structure of the neuron, we can notice that there is the cell membrane of the axon, that is called what? Exolemma. Then there is this cell membrane of your synaptic end bulb. The cell membrane of the synaptic end bulb is also called presynaptic membrane. The cell membrane of the synaptic end bulb is called presynaptic membrane, and since it's a neuron, it's obviously going to control the actions of some organ of the body. The organ whose actions the neuron is going to control, the organ whose actions this neuron is going to control, this organ is called effector organ. Effector organ on which the neuron is going to show its effect. And the effector organ can be what? A muscle, or it can be a gland, or it can be another neuron. Okay. Now the cell membrane of your effector organ is also called the postsynaptic membrane. Presynaptic membrane, postsynaptic membrane. Together, both the membranes are referred to as a synapse, or the literal meaning of this word is what? Junction. The pre and the postsynaptic membranes of the neuron and the effector organ are together referred to as the synapse or the junction. But we can actually see that we have called it a junction just because of their proximity to each other. Is there any actual physical junction between them? Not at all. We can clearly see that this is here and this is here. There's a gap between them. So they're called a junction together, both of them, because of the proximity or the closeness. But in reality, there is no real junction. In reality, what exists between them is a gap or a space. What is this gap called? Synaptic cleft. Not very wide, maximum 10 to 20 nanometers wide only, but nonetheless a gap is a gap. And what is it called? Synaptic cleft, which exists between the pre and the postsynaptic membranes. So this, what we are looking at here, is a synapse or a junction. The pre and the postsynaptic membranes together are called the synapse or junction. In reality, there is no real junction. There is in fact a gap between them, which is called the synaptic cleft. Okay, depending on who is the effector organ, muscle, gland or neuron, the synapse can also be called neuromuscular junction, neuroglandular junction, neuronal junction. Okay, so depending on the type of effector organ, a synapse can be called a neuromuscular junction, which, as the name is suggesting, will be a synapse involving a neuron and a muscle as the effector organ. The synapse can also be called a neuroglandular junction. Here, who is the effector organ on which the neuron is going to show its effect? Some gland. And the synapse can also be called neuronal junction, where the effector organ is another neuron. So that's the three types of synapses on the basis of type of effector organ. Now if we see in this synapse that I've drawn here, the presynaptic membrane and postsynaptic membrane are not in actual contact with each other. There's a gap or a cleft between them. So whenever a neuron receives a stimulus, we discussed about a property yesterday called excitability of the neuron. So whenever a stimulus is received, there will be generation of a mild electrical current of 30 millivolt, that is called action potential, on the neuron, which will travel along the length of the axon till over here. The generation of action potential is excitability, and after excitability, what is the next property of the neuron? Conductivity. So neuron is going to conduct this action potential till what? The presynaptic membrane. But how will the electrical current go to the postsynaptic membrane? Do you think there is any mechanism through which the electrical current, which is present over here on this membrane, traveling from up in this direction? So this membrane is right now charged. It has this potential. How will the potential be transmitted to the effector organ? There is no way right now because there is no physical contact. So what exactly is the mechanism through which the neuron is going to control the activity of the effector organ? The neuron has to release something. What something? The chemical that is stored inside the vesicles. Who is that chemical? Neurotransmitter chemical. So collection of a stimulus over here, generation of an action potential over here, that is excitability, conduction of the action potential over here, triggering release of neurotransmitter, which will attach to the membrane of the effector organ, stimulating it, inhibiting it, or we can say simply regulating it. Okay, so in this type of synapse where there's a synaptic cleft between the pre and the post synaptic membrane, there is no way that the current or the action potential or the impulse or the stimulus, whatever you want to call it, can travel from the neuron to the effector organ directly. That's impossible. So how does the neuron give its impulse to the effector organ? By releasing chemicals called neurotransmitters. So since in this type of synapse, the pre and post synaptic membrane are not in actual contact, there's a gap between them, what do we call this type of synapse as? Chemical synapse. Because what is compulsorily supposed to be released over here? Neurotransmitter chemical. So one classification of synapses is on the basis of type of effector organ: neuromuscular junction, neuroglandular junction, neuronal junction. The other type of classification of the synapses is on the basis of how the presynaptic membrane of the neuron and the postsynaptic membrane of the effector organ are communicating with each other. So if a synaptic cleft exists between the neuron and the effector organ, if a synaptic cleft is existing between the neuron and the effector organ, the neuron must release a neurotransmitter chemical. That's the only option because it is not in physical contact with the effector organ. So neuron must release a neurotransmitter chemical which needs to travel across the synaptic cleft up toward the postsynaptic membrane. The chemical has to travel across the synaptic cleft up to postsynaptic membrane, regulating, which can mean both the ways, stimulating or inhibiting the action of the effector organ. So we can notice that neurotransmitters are not only always stimulating or not only always inhibiting. They can do both the things. That is why a better or a safer word will be regulation. Neurons regulate. They can stimulate the effector organ, they can inhibit the effector organ. In fact, on that basis, they are called excitatory neurotransmitters and inhibitory neurotransmitters. Both of them will be either exciting or inhibiting the target organ, hence they are called regulating chemicals. So neuron has to release a neurotransmitter that goes across the cleft up to postsynaptic membrane, regulating the actions of the effector organ, and such synapses in which a synaptic cleft is there, the neuron has to release the neurotransmitter. Such synapses are actually called chemical synapses. What are these synapses called? Chemical synapses. Why? Because what is involved in these synapses? The release of a neurotransmitter chemical. Now there are two problems, we can say, or properties of the chemical synapses. The chemical synapses exhibit two properties. What are those properties? Number one, synaptic delay. Number two, synaptic fatigue. What is the meaning of these terms? Let me take you back to the diagram here. There is collection of a stimulus by the dendrons, generation of an action potential over here, or a mild electrical current, transmission of that mild electrical current over here. Do you think right at this moment only, when the electrical current is present over here on the axon membrane, will it go and affect or regulate the activities of the effector organ immediately? No. When the action potential is over here on the presynaptic membrane, there will be first release of neurotransmitter, then it will travel slowly and will attach over here, then only the effector organ will be showing its action. So do you think there is a time lag between presence of action potential over here and the presence of an activity in the effector organ? Yes. What is the time lag? The time taken by the neurotransmitter to get released and then travel and then attach over here, because then only the effector organ is going to show its actions. So we can clearly notice that when action potential is generated over here, it reaches very quickly till this place. But then the action potential cannot reach over here because there is no actual contact. So neurotransmitter release, traveling of neurotransmitter, then only there will be effect on the organ. So the time taken for the release of neurotransmitter, the time taken by the neurotransmitter to travel across the cleft, that time is called synaptic delay. Because the presence of action potential over here and the transmission of that, the effect of that action potential over here, there's a small time lag between them. Why is the time lag there? Because the neurotransmitter takes time to get released and then travel. This time lag between presence of action potential on the axon terminals and the effect of that action potential on the effector organ, this time lag is called synaptic delay. Okay, so the chemical synapses exhibit synaptic delay. The time lag between the arrival of action potential on axon terminals and the response shown by the target organ. I think you got this. The time lag between arrival of action potential on the axon terminals and the response shown by the target organ. Response to this action potential. This is the time taken in releasing the neurotransmitter. That'll need a few moments, releasing the neurotransmitter. So this is the time taken in releasing the neurotransmitter. And the time taken by neurotransmitter to travel across the synaptic cleft. Not a very significant time. I mean, we can't notice it, but nonetheless, there is a time lag. The time taken by neurotransmitter to travel across the synaptic cleft. So this is called the synaptic delay. That will be one problem with the chemical synapses. What is the other problem? Synaptic fatigue. Have you ever noticed that when you hold an ice block in your hand, for some time the ice block is going to feel very cold, but after some time we say our hand becomes numb. What is the meaning of that numbness? That numbness is synaptic fatigue, loss of sensation. Let's say I am continuously stimulating the dendrons. There will be continuous traveling of action potential down and continuous release of neurotransmitter. Do you think the neurotransmitter is stored in infinite quantity here? No, it's limited. So if there is continuous collection of stimulus at the dendrons and continuous release of neurotransmitter at the synapse, there might come a time when the neurotransmitter supply gets exhausted. Khatam ho gaya, finish. After that, if you keep giving stimulus to your dendrons, do you think the neuron will be still stimulating the effector organ? No. So this is that thing when you put an ice block on your hand, the neurons are stimulating your brain about the temperature of the ice block. But for how long? For a limited time. If you don't remove that ice block from your hand, the neurons which are taking the information from your hand to your brain, they will finish the neurotransmitter because the entire neurotransmitter would have been released. So after that point, your neuron is supposed to have undergone synaptic fatigue. It is still collecting the stimuli, but is it sending any responses to the effector organs? No. Why? Because there is no neurotransmitter left. So what is this called? The stage of synaptic fatigue. Okay. So synaptic fatigue is the neuron continuously receiving a stimulus at its dendrons will continuously release the neurotransmitter from its synaptic vesicles. Finally, finishing the entire stored neurotransmitter. Finally, finishing the entire stored neurotransmitter. So, it now fails to send any information to the target organ. Is it the same like muscle fatigue that you have studied in locomotion and movement? Yes. In muscle fatigue, the muscles proteins get denatured because of lactic acid accumulation. But in synaptic fatigue, the neurons stop acting because they are finished with the neurotransmitter. Now it fails to give any information to the target organ. That's the stage which is called synaptic fatigue. What are you supposed to do after synaptic fatigue? Remove that thing, the ice block from your hand. Allow your enzymes to digest the neurotransmitter that is released over here. Once it is digested, the digested components are absorbed back by the neuron and converted back into a fresh neurotransmitter. So after 1 hour, if you'll hold the same ice block in your hand, will your neuron be again able to stimulate your brain about the temperature of the object? Yes, because in the meanwhile, the neuron would have got back the neurotransmitter or synthesized new maybe. So these are the two problems with the chemical synapse: delay, fatigue. In spite of having two problems, chemical synapses are the most common in the body. Even though there are two problems here, delay and fatigue, but chemical synapses are the most common synapses in the body. So why do you think are the chemical synapses most common in the body? Because of an advantage that they have. The advantage is they allow unidirectional impulse transmission. What is unidirectional impulse transmission? Only from the neuron to the target organ. Only from the neuron to the target organ and not the other way around. Look at the picture again. Here, chemical synapses allow neurons to control the target organs or the effector organs. Do the effector organs also have something that they can release to control the activities of the neurons? No. So there is information transfer in this direction, but is there any information transmission in the opposite direction also? No. This allows the neurons to control the effector organs while not getting affected themselves by these organs. So that neurons will become our control and coordination centers. Since neurons are our control and coordination centers, they should be able to control the effector organs and they should not get affected by the effector organ themselves. So how is that possible? Only because there is one-way transmission of information. The other way doesn't occur. That's the advantage, the biggest advantage that the chemical synapses are giving us. They only allow impulse transmission from neurons to the target organ, making the neurons control and coordination centers of the body. Control and coordination centers of the body. Because if the neurons themselves are also getting affected by the target organs, then the neuron is not the control and coordination centers. If I am teaching you and you're also trying to teach me, then things cannot work. It has to be a unidirectional flow of information. Then only things will go smoothly. So that is what chemical synapses allow. What other arrangement, by the way, can we make on the synapse? Let's imagine I make a protein here which connects my presynaptic membrane to postsynaptic membrane directly. If I make a protein here, now is there any synaptic cleft? Technically, no, because if we see, the membrane of the neuron and the membrane of the target organ are physically in contact with each other with the help of this protein, and proteins are conducting in nature. So that action potential which was here, can the protein immediately take it to the postsynaptic neuron? Yes. Or postsynaptic membrane? Yes. Instantaneously. Making sure that there is no delay. And since neurotransmitter is not involved here, इधर तो प्रोटीन की हेल्प से डायरेक्टली करंट नीचे जा रहा है,
तो अगर न्यूरोट्रांसमीटर इन्वॉल्व ही नहीं है तो ऑब्वियसली साथ में यहाँ पे क्या नहीं होगा, नो फटीग ऑल्सो. So no delay, no fatigue if I join the presynaptic membrane to the postsynaptic membrane with the help of a protein. The protein is conducting in nature, and now if we look at this structure where the neuron and the target organ are connected with the help of a protein over here, this type of synapse is called electrical synapse. Okay, so if the pre and the postsynaptic membranes are joined by proteins, the synapse would be now called electrical synapse. It's not a chemical synapse anymore. It's an electrical synapse in which the protein will actually help in immediate transmission of the action potential from the presynaptic membrane to the postsynaptic membrane, in which there is no delay and there is no fatigue. There is no chance of synaptic fatigue because neurotransmitter है ही नहीं ना, तो fatigue किस चीज़ का होगा? So do you think electrical synapses are better? Looks like that. But what is the problem with the electrical synapse? If action potential can come down, can it go up also? Yes, because the protein will allow bidirectional impulse transmission. So these synapses allow bidirectional impulse transmission, and that's a problem because now the target organ also will be able to control the activities of the neuron, and that is what we don't want. So should we actually have electrical synapses in the body? No. So these synapses do not exist in the body. We have studied cardiac muscles. Cardiac muscle fibers are connected to each other by intercalated discs. Those intercalated discs are proteins that allow the action potential of the pacemaker to travel from one cardiac fiber to next fiber in both directions. If this is your heart wall, here's the pacemaker currents can come down in this direction. But if the pacemaker is not functional, AV node can generate the current and bring them down and also take them up in this direction. So can you see cardiac muscles में current transmission इधर भी हो रहा है और if needed opposite direction में भी हो सकता है, ऊपर की तरफ from the AV node. अभी नीचे हो रहा है from SA node to AV node, but if required वापस ऊपर opposite direction में भी हो सकता है because cardiac muscle fibers के बीच में क्या है, intercalated disc, और intercalated disc क्या है, gap junctions और proteins. तो इवन तो न्यूरॉन्स में तो इलेक्ट्रिकल सिनेप्सिस हमारी बॉडी में नहीं है, बट द गैप जंक्शंस और इंटरकैलेटेड डिस्क of our cardiac muscles, they can be considered as examples of electrical synapses in the human body. Okay, so that is it guys about the types of synapses. There are two types of synapses possible on the basis of what is allowing the transmission of impulse from neuron to the target organ, neurotransmitter chemicals or proteins. On that basis, chemical and electrical. Function wise, electrical are better, but chemical is what we have because they allow neurons to control the target organs because of unidirectional impulse transmission. And of course, this classification of the synapses, neuromuscular, neuronal and neuroglandular junctions on the basis of the type of effector organ. Okay, so that's it then for now, the various types of synapses and how the neurons connect with the target organs. So I'll continue in the next lecture with the various types of neurons on the basis of their functions. Till then, keep studying, keep sending if any questions you have in the comment section on the video, or you can always contact me on my phone. Okay, that's it guys, thank you, bye bye.